Hello guys. Okay, today we have exercise number 11, substitutions and equations. But first we'll talk about the previous thing. So how was it going?
We had to do math 2 hours every day,
Yeah, that's natural. Yeah, because unfortunately we didn't touch this part in mathematical, right? In mathematical lessons, but we have to use it in physics more than in mathematics. So at least we got some math here. But as a result, have you come to something? At least some understanding?
I think the kids now slightly understand what slope is. What's a slope?
Change of water type on X.
And what is a derivative?
It's a slope.
What kind of slope?
Instantaneous slope.
Okay, good enough.
So did you got the answers to the questions?
Yeah, we solved the first two. The second one, I did
The third one.
Oh, we didn't. Actually, I didn't even. I looked at the notes and I couldn't understand it, to be honest with you.
The third or the fourth?
Question?
The third was, what is acceleration formula? There was a distance, and the number 2, distance is changing according to the formula.
Yes. So first one we did the second one. The third one was the pipe where the water stops. I didn't remember what you were asking for there.
Acceleration.
Sorry. Can you repeat the third question? We'll revisit it. Okay, write it down for me. Would you mind?
The question for number 2 was, what is the formula for velocity?
No. The second one we know. We did the second one, and the kids recognized that it was free fall formula.
Okay.
They recognized it.
So acceleration is 9.8 then, right?
Yeah, that's right.
Okay, so calculate how hard and force or pressure, if you define it, is the shock when kitchen tap is closed sharply.
Oh, the force?
Yeah, the force.
The force.
The force.
When it's closed, okay.
Or the pressure, if you wanted to define it, no problem. Maybe easier. The pressure is easier, but it's anyway. You have to define the force first, right? So you didn't do it? Okay, try to do it. It's nice exercise.
Yeah.
Okay.
Yeah, we'll try.
Okay, guys. Okay. So now we'll continue a little with the previous one, just to have some understanding, a little more understanding of what we're talking about, and some for you to understand that it's pretty paradoxical. Again, paradoxes are everywhere in mathematics and logic. In spite of some people claiming that there are no paradoxes in mathematics, it's wrong totally. Mathematics is full of paradoxes, just they always try to hide it. That's the way, because it's difficult to deal with paradoxes, so they try to hide it. So, and the paradox that we're dealing right now, right here, with differentials and everything, is pretty obvious. We're talking about something like differential, right? Like dx, right? Something that is close to 0, very close actually, almost 0, but not 0. And this is already a paradox, because how something can be anywhere close but not 0? So there's no way that you can differentiate one, so like separate dx from 0, because it's so close that you cannot separate it, and still they are different. So it's paradoxical in the beginning. And the results of them are also paradoxical, right? For example, we have 0, right? If we have like 0 plus 0, what will be the result? 0. Like 3 zeros, what's the result? 0, right? Like 5 0. 0. Now, if we try to find out what would it be like for example, 0 plus 0 divided by 0.
That's That's zero.
Huh? Here is 0, right? 0 divided by 0, well, at least something like 1.
What?
No, they are the same. They are the same, right? We're talking about paradox. It's not like that some rules. It's not, there's no strict rule. The strict rule in arithmetic is you cannot divide by 0. But if we try to do it, like for example, here a 0, here a 0. Should be 1, right?
Yeah.
Yeah, but if we go another way, like 0 plus 0 divided by 0, like, so it is what? It equals 0 divided by 0 plus 0 divided by 0. You understand that, right?
Yeah.
The fractions. So here's 1 and here's 1. So it is 2. This is 1, this is 1. Again, if we decide like 3, 0, like 3, 0, it is 0, right? So 3, 0 divided by 0. What do we have? Like 3. Right?
That's actually correct.
So that's why because we got indefinite results, we got different results when we're trying to work with these zeros, right? That's why it's not allowed to divide by 0 in arithmetics. But if we substitute dx instead of 0, it will be pretty different. Like 2dx, right? It's not equal to dx, right? Like if it will be 0, it will be 0. But dx is almost 0. 2dx is not dx. 2dx are 2dx. Like dx plus dx is what?
X. Yeah, 2D.
2dx. Yeah. So we have the same thing, and we can calculate this like if you have dx plus dx divided by dx,
Yes.
you have what?
I can't. Oh, sorry.
2, right?
Sorry. Oh, yeah.
2dx divided by 2, right? So interesting enough that we're working almost with zeros, but still we don't have this thing. Interesting that you can actually, because they're almost the same. Look, they're almost the same, dx and 0, almost, but not exactly. So it's almost the same. You can work with the things like 2 zeros, 3 zeros, you know, 0 square, and all that. Like 0 square divided by 0, it is 0, right?
Divided by 0.
0 squared divided by 0. Maybe like dx squared divided by dx, it is dx. So it is correct. This is prohibited. But what's the difference between just the notations? Here we use dx, here we use 0.
No. The difference is very clear.
Okay.
You can multiply by 0, but you cannot multiply by dx. When you multiply by dx, dx remains there. When you multiply by 0, yeah, of course.
What do you mean? What do you mean you cannot multiply? You can multiply.
No. What if you have, let's suppose 8 times 0 equals 0. 8 times dx does not equal 0.
Sorry, what?
Say it again.
Why?
8 times 0, 8 times 0 equals 0. And 0 disappears. I mean, 8 disappears, right? And now 8 times dx,
Okay.
8 or 8, whatever.
8 dx. It is.
8
It's
dx.
not dx.
No, it remains itself. That's right. So you cannot just divide by 0 because of the value.
So this is because of this rule. This rule disrupts the situation, right? So this rule. But
Not rule, it's common sense, right?
common sense.
Yeah, so this is
Okay.
one of the axioms.
Okay, trust me, there's no common sense in paradox. You know, this paradox is not common sense. It's very interesting stuff. So it is a rule like this. Yes, it is a rule of arithmetics, and that's it. But it's very interesting to understand why 8 dx is not dx. It's still 0. The same thing, by the way, with the zeros goes with this infinites, right? like infinite plus infinite, it is like infinite, right? Still infinite. It's not. So like 3 infinites is still infinite. So they're very similar, 0 and infinite, right? And again, you can talk about infinite like 1 divided by dx. It's approaches to infinite thing, but again, it is not that infinite. It's something else. So just for you to understand that this is very paradoxical. That's the only talk. So this because of this rule, and rule are something that actually to be broken actually, because rules are very interesting things. They never absolute. They may work in one field. They will be broken in another field, and that's where we goes to this thing. So another point of this, we talked sometime about this. Like for example, 1 square. What is it? The result. 1. 1 to the power of 5. 1. 1 to the power of n whatever.
1.
Still 1. So 1 to the power of infinity.
1.
Huh?
1.
Is it really 1? Actually, there's a thing that I mentioned in the previous thing. That's this guy, Leonard Euler. Yeah, he does this thing. 1 plus 1 divided by n. And n is approaching to infinity. So 1 divided by almost infinity, it's going to approaching 0, right? So it's almost 0. But it is power to the power of n, and n is goes to infinity. So this is almost 1. This is almost infinity, and still this equals to Euler number. Remember, it's 2.7 something. This is proven in mathematics. So there are lots of paradoxes connected with this stuff, and you just have this in mind. So dx is a very paradoxical thing, and also all this calculus, which is the algebra of differentials, the infinitely small and infinitely large things, values and numbers. Now we'll talk about something that is very helpful in calculations, which is called substitutions. Substitutions. Like for example, we have a function like this.
1 equals.
This is e. This is called exponential. E to the power of something. It's called exponent, the function. I think I told, right? I think I spoke about this, yes? This is a Euler number. So if you have this kind of thing, and you want to get a derivative from this, what would be derivative?
It would be x e to the power of x minus 1.
Did I mention it, Anton, or not?
No, you mentioned it. Of course, yeah, you mentioned it, but...
Okay, no, this is like this. The derivative is the same. It is argument. It is not a constant number. This is argument of the function.
The only function that doesn't change the derivative.
This is function of x. X is argument, so it's changing. It's a variable. X is a variable. This is function of the variable x. X is argument, y is function. So the derivative, or sometimes they mark like this, by x, it is still the same. It doesn't change. This is one of the very interesting and very interesting feature of this function, which is called exponent. Now we have something a little more difficult. E to the power of x squared. Again, this is a function. How to calculate this thing? derivative. We want a derivative. So how to find out this? And here comes a very useful thing which is called substitution. We substitute something with something else. So we have x squared. This is more complex than something. And we know that derivative from this is very simple. So we...
The function,
Pardon?
is it e to the power of x squared?
Yes, x squared, yes.
Okay.
So what we do? First we do substitution. We do like this. We invent other function like z, which is x squared. So we substitute x squared by z. When we substitute like this, what we will have? The function will be like this.
E to the power of z.
Yeah, e to the power of z. So y becomes the function of z. Z the new argument. So we can calculate the derivative of this, like it's easy, right? Derivative by z. It is the same.
Yeah.
E to the power of z. Like this, right? The same thing. But we don't need this. We need this, right? So how we do after? So this is a very simple thing which goes from differentials. Like if you want to calculate dy divided by dx, this is a derivative, right? Definition of derivative, right?
Rise over run. That's a rise over run.
Oh yeah, because it's a y over x.
Exactly. Yeah.
I don't know this term. What you said again?
It's slope.
No, it's when you calculate slope, the terminology in English language is it's rise, which is a change in y, over
Okay.
run, change in x. So change in y is dy, change in x is dx. And the kids know this terminology, rise over run. That's what the books use.
That's what they teach in school.
Okay, that's a little new for me. I didn't get the sentence you got. Okay, we'll talk a little later. No problem with this. So anyway, it's dy divided by dx. So you should approach it like this. So dy divided by dx. dy and dx both are almost zeros but not zeros. Y is from function y, x is from x. So, and we can write this because we can use them as regular variables, right? We can work with them with these d differentials. We can write this dy divided by new variable dz, and here we write dz divided by dx. You see, it's the same because this we can, right? We can, what's this cross? What's the term?
Cancel out.
Cancel, yeah, cancel out. We can cancel out, right? So it's little trick, right? You see that? So it's the same thing. But dy by dz is exactly that, right? And now all we need to calculate this derivative, and dz by dx is the same as z
Write it down.
z prime x, and it is
Wait, I can't see the glayer's in the way.
okay. Okay, I'll write it here. Derivative dz by dx, it is the same as z prime by x. It's just denotation, right? And it is, let's calculate it. We know what z is, right? z is here, x squared. What will be the derivative from this? Z by x.
Say.
Did the derivative of x squared is 2x?
2x. Right?
Yeah.
And dy by dz, it is this one. So we can write e z multiplied by 2x. Right? You got this? This is from here, and this is from here. And z is x squared. So we can write it ex squared plus, multiplied by 2x.
Flowers.
Can you see this? Yeah, you can. So this is the power of substitution. So if you find something that is difficult to calculate, right? So you define this, substitute this by new function like z, whatever, new variable. You can do this many times. Many times. Like for example, you wrote it, right?
You write it down.
Whenever I do a base or something, it does something.
Like the same thing, like y is the same. Let's e like x and like what?
Oh, wait, Papa, so e to the power of x squared is e to the power of 2x.
Why not like this? E to the power of e and to the power of x squared.
Wait, oh god.
It's an amazing function, right? So what we do, first of all, we do like this. It's z equals like e x squared. This is first substitution. And then we put some u for this. Is x squared.
Wait, 4 equals x squared, that means...
Yeah.
It's u.
So we have, yeah. So we have this, right? E to the power of, yeah, e to the power of z, right?
Wait, we're using z again? I thought it would be e...
Who cares? It's the name of the variable.
I thought it was going to be e to the power of e to the power of u.
And z is e to the power of u.
Oh yeah!
So now what we can do? The same thing. If we want derivative of dy by dx, write it like this. dy by d first is z, dz by du, and du by dx. So again, here I may cancel, right? But still, this is dy by dz, this is dz by du, and this is du by dx. So it's, you may write it like this. Z, u, and, sorry, it's z. And u,
Yeah, but
u by x. And just the notations, but still, all you should remember this. It's easy thing, you just write addition things, like they cancel each other. It's still dy by dx, but they have different meaning. This is one derivative, another, and another.
Oh yeah!
And you can calculate it, just make it and just calculate it at home.
Okay.
you can multiply.
Write it as your exercise.
The same variable, right? So you understand this?
Yeah, I'm saying it across them. Done it before.
So it's very powerful, you see. It's a very powerful tool, and it allows you to calculate like lots and lots of different and very complex derivatives. Also, there are some other rules, like probably you already talk about this, that you know that derivative of like constant, right? It is 0 if it's constant function.
Guys, pay attention. Do you remember this?
Oh
What's the
yeah,
derivative of constant?
slope.
And also, if you have different functions as a sum, like y function is sum of other functions, like f at x plus like phi of x, whatever. So if you want to calculate derivative, it will be derivative of first function plus derivative of another function. There are simple rules, just you have to remember them too. This is first, this is the second. I believe that Antosha remember that, so just remind the guys these things when you're calculating.
Is that y next or p?
It's y. Y.
Oh, okay. Just wondering. So then when I'm writing it down, I don't confuse.
You wrote it? Okay.
Oh, no, not yet.
Okay.
I'm almost done. We're done.
Okay. And now let's use the same rule, the same method of substitution. It's very useful in calculations of integrals. And integral, remember, it is totally inverse operation to derivative. If you have something like function which is integral of some other function, it's written like this. It's written like this. Now we'll talk about why it's written like this. This is a sum, like infinite sum of infinitely small things, like dx, right?
Is that a paradox?
It's all paradoxes, believe me, but we're not talking about paradox right now. It is a definition, right? Or actually denotation. But the definition is that if you calculate derivative from this, right, it will be exactly the function that goes under integral. This is the definition, because integral or y, right? This is called indefinite. It's called indefinite integral. So this thing, this function, actually, it is inverse to derivative. Inverse. So you can calculate back and forth. If you have this, right, you know that the derivative of this will be this, but the integral of this is this. So this goes this way and this goes this way. That's why those things are inverse. F and y. F and y. You see, derivative of y is fx, and again, integral of f is y. Go back and forth. And how it comes? Just let's find out. Let's find out. So this is actually a definition, right, of integral. Now, derivative of y by x, what is it? We know that is dy divided by dx, right? And it equals this fx, this. So it's the same thing. We just rewrote it. The same thing. Now, because we can work with these dy's and dx's like regular variables, we can write this. Dy equals f of x multiplied by dx. Right? From here, huh?
That makes sense.
It makes sense, right? Now, this is, again, so differential of y is differential of x multiplied by function f of x, right? Now, what is dy now? What is it? Like, to understand what is dy, it's the same as to understand what is dx. It's the same thing. They're just differentials of some variables. This is one variable, this is another variable. They're very much the same, but just different in values, right? So what is dx? We have the x. You can see, right, this? Yeah. You can see x-axis, right? And you can find some small interval here, which is dx. Dx, right?
Yeah.
We can add to this dx another dx. Will be this, right? Then another dx will be this. Then another. Lots of dx's. So if we summarize all dx's, we'll have this thing. Sum. This is the letter. What is the letter of this Greek letter? I forgot. What's the name for this? Maybe you remember, Antosh?
Sigma.
Oh, sigma, right, I forgot. Sigma. This is sigma, Greek letter sigma. So, but anyway, it denotes the sum of infinite sum of all the x's, and the x's are almost zeros. But when you have them in infinite, it is like something real, right? So, infinite amount of them, right? And just look at this axis, and you add all these x. What will happen if we add add all of these dx's along this axis x, what will happen? What is it if we add all these dx's? What do you think?
Infinity. Yeah.
What would it be?
Infinity. Infinity.
Yes, infinity, yes, but can you see that it's the same as the axis itself?
What do you mean?
Yes.
Because the axis consists of these intervals, small intervals. All of them, all these axes consist of these small things. So this is infinite sum of infinitely small intervals, right? And the way how they denote it, it is this. It's like this sum goes to this, and this is dx. And because it's the same as the whole x, it equals just to x. So x equals to. It is the same as x's. And this is one of the formulas. If there's 1 here instead of function, you see this integral. If there's 1 here, it's just 1. Like you can write 1, nothing, everything will be the same, right? So this integral, it equals to x. Integral of dx, just dx, no function, just 1. The function, constant function, equal to 1. So it's 1. It equals to x. But if we have this, you got the idea, right? Yes.
Yes.
But if we have this for x, we have the same thing for y. If we summarize all of the dy's, we'll get the axis, what axis? If we summarize all dy's, so we do that. dy. What axis would we get in this case?
X's?
Axis.
Y-axis. Yeah. Yes, you would get the y-axis.
Y-axis, exactly. So it is y equals to dy, but dy here have fx dx, so it is fx dx. So that's why we have the formula. That's why. This is the infinite sum of small, infinitely small differentials dy's. This is the sum of infinitely small dy's, and this is y. So think about it, and when you think, you'll understand the deep connection between derivatives and the integrals.
No, but
Yes?
I'm a little.
Yeah?
Oh, okay. Yeah, no, never mind. That's okay.
Yeah, that's okay. Actually, this approach that I use is a little different from standard approach. There's a standard approach which in calculus, which gives you that the x and the x is something very liquid. It's going process of approaching zero, approaching, and never approaches it. This is a standard approach of calculus. But there's another approach which is called non-standard, exactly called non-standard, which says that the x is the something that is already there, but not zero. So it's a little more paradoxical. Both of them are paradoxical, but one is like liquid, another is like solid. But they are almost the same. But it's much easier in many ways to think about differentials like stable things, not like approaching something or whatever. It's a simple thing. Now we'll talk about substitutions and integrals. How to calculate, how to use these substitution integrals. Like for example, it's the same thing, substitution. So we invent some other function. Like we have like some difficult, like for example, like plus 2, like to the power of 7, to the power of maybe 7, right? And
Isn't that x to the power 4?
like what? Like for example, we have such. No, x3. Let's do it like x3. So to calculate this? There are different ways to calculate it. There's simple thing like you just multiply, open this thing, but the brackets, right? But there's a big power, right? Big number here, 7. So already it's made it pretty difficult to calculate. There's lots and lots and lots of numbers of expressions. So it's difficult to do that. So if you don't want to do that, there's a way when we use substitution. So what do we do? Like we substitute, like for example, some complex thing. We substitute this thing under the brackets. Under the brackets, right? Oh, maybe, yeah, under the brackets, as z. So z equals, we make substitution like this. Z equals 2x to the power of 3 plus 2. That's what we do, right?
Okay. So it's z to the power of 7.
Yeah, to the power of 7, yeah. So what we have then? We have here z to the power of 7, but here are still x. We need to change these things somehow to new variable, substitute. It's z to the power of 7 multiplied by something. Let's do that. Let's calculate derivative from this. So dz by dx, it is, guys, you should know, there's a sum of these derivatives. Derivative from constant is 0, and derivative of this is of this one.
You know the derivative of x cubed.
3x.
3x.
N minus
To
1.
the power of 3 minus 1.
And
Which
so
is minus 1.
To the power squared. 3x.
squared, right? So we have this, all right? What can we do? We can write from here that dz multiplied by dx, right? It's 3x 2 dx, right?
Wait, dz?
From here.
What squared?
Yeah, you know, they never taught us this technique.
Hey, Papa, what's that thing beside the x squared? 3?
3x squared times dx.
So we just, we multiply by dx both sides of the equality, right, of the equation. So we got dz. dz is 3x squared dx. From here, but we have this and we have this here. So we need to find out this part. So we can find out that x squared dx equals 1/3 dz. Right? From here we get here. Can you see this?
Oh yeah, I
Right?
understand.
So when we have this now, what we needed here. So we can put it here. It is 1 divided by 3 dz. This you will know from derivations, and when we calculate, can be easily put here. So we have this 1/3 integral of z7 dz, and this is pretty simple. You should find out what function you can imagine that when you take derivative it will be z to the power of 7. What do you think? What function would it be? Because there's inverse thing. So what function can we find out? Just imagine some function that by z, function that derivative from this will be z to the power of 7. Can you imagine this? Remember, to get power 7, right, we need more power, right? So like 8.
Oh yeah,
Okay. So it will be z to the power 8 and some multiplier to remove this multiple 8.
What's the derivative of that to the 8? What's the
8z to the 7.
Yeah, do you see that? 8z to the 7.
Oh yeah.
But you want z to the 7.
Oh, z over 8 to the
Tell Zeta.
Oh.
Z over 8 to the power of 8.
No.
Yeah, 0 over 8, yeah. Well, like this.
I meant z to... Oh yeah.
So this is this. And 1/3, we have 1 3 by 8. 24 z to the power of 8. You got this?
Yep.
So, and z, we have z is this, right? So we have 1 divided by 24 x plus 2 to the power of 8. And this is the result.
Wait, 1 over 20. What's that H mark?
That's mine. we got the result.
Usually it's like at the end.
No, it's not factorial. No.
What's QED?
It means problem complete.
Oh.
Yes, just whatever you may. So that's how it goes. It's very useful, and it's used in many things. But it some work of art needed. You know, you need to understand what substitution you have to make, and if you find out what's the way. So the art of calculating integrals, it's an art. It's not like a strict science. There is no like straight algorithm how to do this. You need to think what to do. There are some other powerful methods, but we will not talk on them right now. Maybe we'll touch them a little later. But substitution was one of the really powerful one. So you got it? I may remove it. Okay, so use this substitution. It is very useful in both derivatives and integrals calculation, right? In derivatives, it's extremely useful. It's almost allows you to calculate anything you want, almost anything you want. In integrals, it's very useful, but not everywhere. So sometimes it's difficult. Some integrals cannot be taken in the function form at all. Not some, many of them, actually. So derivatives, you can calculate almost all of them, almost all derivatives that you need, and write it like in mathematical way. Integrals, many of them can be calculated only in numbers, but not in functions. Interesting enough. So it's complex. Now we'll talk about differential equations. Differential equations. What is differential equation? Differential equation is an equation like regular mathematical, but it admits that there are maybe some differentials there. So if you see any differential equation, it is a differential equation. That's all. Very simple.
So with so a differential equation is an equation with differentials?
If you find some differential in equation, it is differential equation. That's it.
What's a differential?
Like for example, differential is this, like dx, dy, dz. This is differential. So if you have this, dx equals 0, it is a differential equation. And like if you want to solve it, what do you think? So x should be a function of something, right? If a differential x is a function of something. If you have that equation, what do you think a solution is? X equals what? This is the first and simplest differential equation.
Over d, that's 0.
Dx equals 0.
What derivative of what function?
Constant equals 0.
So
Constant equals, that means x equals 0.
Constant, yes. But you're right, constant.
no, stop. Just
Right. So usually like they write like this. They just C, like constant. So yes, this is the solution. X equals C. Solution of this equation. This is solution. It's a constant function. Now let's try something else. Dx equals like 5. We need to find function x, which when you...
Derivative is 5, right?
Yeah.
But what's the function that you use?
All right, that's the right question. You should find out what's the argument actually. Yes, we write dx, but there should be some argument, right? It's x is a function, so it should be a function of something. So we should. It's not exactly correct to write it like this.
Yeah, to say dx equals 5. Dx is an infinitely small number.
Yeah. Right. So this is already not correct writing. So just don't do that. So usually they do it like this. So because they need to know what function it is, so they write it like this. So you can write here dx by dt equals 0 and will be this solution. This is more correct writing for this, because the argument is mentioned, the argument of function x. X, we're looking for x as a function of t. So, and this derivative equals 5. So in this way x will be, guess.
Derivative of what function equals 5?
So we need to find some function, derivative of which will be 5.
Do they call C? What's the derivative? I'll give you a hint. What is the formula for a linear function? What's the derivative of a linear function? This function. A. Do you see this? Cut that. So what's a linear function?
It's a straight line.
Cut a formula for general linear function. What's the derivative of that?
It would be A.
A. That's right. A. Look at that. Oh. Here we have 5, not A. So replace what with what?
我就说背。
Be quiet. You be quiet. Gotcha. Gotcha. Give me a. Gotcha.
The answer would be 5.
No. Well, it's a constant. No, they don't know.
They don't know. Okay, whatever. So let's try 1 first. Something that as a result of derivation will be 1.
What's a linear function? Look at me. What's a linear function? I didn't ask that.
Okay, guys. Okay, it's x.
Huh?
It's just sorry, t. It's just t.
Huh? So, you instead of A, you want what? It's right there. What do you want? Kacha. This is the derivative. What do you want? So,
Yes, guys, okay, just forget about it. Just you can make this calculation later, okay? So this is just t, because why it's t? Because when you
what
want,
is one?
when you put this function x equals t here, right? So we take a derivative from t, it will be 1, right? So if we,
It's X.
No.
x prime from this function t equals 1. So this equals 1. If we put 5 here, it's a multiplier, right? 5. It's the same thing. 5t, it is 5 here.
Yeah, one of the things that's confusing to them is that it should probably be dy over dx. That would be a little bit.
Yes, I know. But this is like, I'm sorry, it's intentional. So we need to understand that all these variables can be exchanged. Yes. So just work with it, and you will got easy with this. Okay. So this is new argument t. It's not y and not everything like this. Okay, but so it will be 5. So this is like easy things. Let's try this and maybe a little less confusing variables, right? For example, we have this equation dy by dx, right? Now easier, right? Equals x. So we need to find some function which, when you get derivative of it, will give you x. And what is it? Thing. What is this function? Any guess? So derivative of this function gives you x.
We couldn't even do the linear function. I don't think they'll be able to do this one.
Okay. Okay, so maybe. Okay, maybe we'll do that then. Maybe it's easier. The same function. If you give it derivative equals to the function itself.
Derivative equals to a function.
Any guess? What function would it be? This is differential equation, yes, because we have differentials here. So, and you see,
Funny name.
derivative from this function gives you the same function. So when you get derivatives, the function does not change in this. Still the same function. What function can this be?
Look in your notes.
Yeah, look in your notes.
It's from today.
I know, this one.
It was literally the first thing we talked about.
Okay, guys, just you follow? Yeah.
Y of x equals e to the x.
Yeah. Exactly. So this is the solution. But also, if you think about a little, so they're like any constant here, like c, right? Multiplier c, it gives you a solution too, because if you put it here, the c just goes here, and you have c y equals c. So c you may add as a multiplier here. Still be a solution for this. Not only just e to the power of x, but also c multiplied by x. And also you can add another constant here. So this is c1, this is c2, another constant here, because when you get derivative, no, here it cannot be. I'm sorry, that's a different thing. So this is the solution now. And just one more example, maybe a little more complex, but still.
But why the constant? Why can you not add the constant?
Why you cannot add the constant? Because if here will be constant, here will be 0.
Yeah, no.
That's why you cannot. And now a little more, like just for guesses. There are also second and third and whatever derivatives. You can do one derivative and another derivative of it. So you can take one derivative and then try to get another derivative of this already. So you can make many derivatives for one function. So it is.
Oh, Papa, so
Just listen.
So it's called double prime or 3 primes or whatever. So you may continue this derivation more and more and more and more. And integration too, by the way. You can do this and that many times. And it's also, the notation is also like this. d2y by dx squared. That's just the notation. Just remember this. 2 comes here at the top, but here at the bottom. A little different. It is the same as d by dx of dy by dx. It's another denotation. And that's why it gives square here, because d and d here doubles. You see, double d, and here is the square. Those are just denotation. Just look at them, think about them a little. But well, this means the second derivative. It's called second derivative. And now the another equation like second derivative of y by dx equals y.
Oh wait, is it this some questions?
Yes, this is just, we make examples. Just if you look at this and this, you can compare, right? Because we have this thing here, right? So whatever times we give derivatives from this, it still be the same. So the solution for this, it's still c look at here.
You can do anything for the numerator, but still equals c.
No, that's not what it is.
So these are simple differential equations. Some of them are very complex and do not have actually solutions in regular functions. So it's a big deal to get this. But differential equations are the basis of physics, because all equations of physics, whatever you talk, like gravitation, physics of gravitation, physics of quantum mechanics, or whatever, quantum fields, they all differential equations. More complex, of course. And when you solve them, you found some solutions that actually allow us to describe this world this way or that way. So they all differential equations are very powerful. But unfortunately, they cannot be solved like forever. Sometimes we have to deal with difficult other ways how to do things. Also, in addition to this, there's a very simple thing. Remember this derivative from sine. What is this? Remember? Sine. Like, for example, we can think that maybe y, it is a sine. Sin, right, of x. If you get first derivative,
Trigonometric function.
it is cosine, right? And the second derivative?
There's no difference?
No, there's a difference, but it's still a trigonometric function.
Second derivative from cosine, it is minus sine, right?
Oh yeah.
Right? So, and y is sine, and here is minus sine. So we can think about something interesting, that if we have equations like this, not y but minus, right? Like this, sine will be a solution to this, because double derivative gives you minus sine, and here is minus sine. So you may think about some interesting things here.
Cosine is a solution too.
Why? Is it the opposite?
And cosine, yes, sine and cosine, yes. Okay, so guys, now questions and questions from me then.
Yeah, actual questions or examples.
No, that was supposed to give you an example.
No, just any questions, guys.
On the right now, you ask me that questions. It's only questions.
Oh yeah, you just hit me out.
Questions?
Oh yeah.
No questions.
Okay, then I have questions to you. First, the first question.
No.
You're ready to write, right?
Vita, come on.
calculate derivations from that kind of functions.
Derivatives.
Derivatives, yes, sir.
Huh? Yeah.
This is a power. X to the power of 3 plus 5. Then another one. Oh, sorry. Okay. Yeah.
Logarithm.
This is called natural logarithm. This just remember that the derivative from natural logarithm is 1 divided by x. This is a function inverse to exponent. This function and this function are inversed. We won't talk it right now, but maybe sometimes later. So two derivations of this. Then, so this is derivations, right? And this is try to calculate integrals by substitution method, right? By substitution. And integrals are like this.
Wait, oh, this is the second question.
Yeah.
Wait, is that 2 signs? I mean, the definite exponent.
It's an integral, open bracket.
So this is 8 by x to the power of 7. This is x to the power of 6. This is another number to the power of x.
Wait, what's that second one to the power of?
8 multiplied by x to the power of 7 plus 8. Here is x to the power of 6. Here is another number e to the power of x. Here's 5. So calculate these integrals by substitution.
Yes.
You've written the first, right?
Yep. I should look at that and see what you find here.
It just leave it a second pair of brackets.
Second pair of brackets, yeah. The brackets was in brackets.
And here just solve the equations.
Oh, but is that dt squared?
Say it again?
If there's that dt squared.
I can't see.
Yeah,
That just means second period. And we already know the answer to this one.
To this one, maybe not. Just let them think, okay?
Okay.
And also there are many solutions, so just think about it. So
Did it? If you just paid attention, did already.
so try to get the most generic solution to everything. Just think about it. What can be a solution to this and to this? There are two equations. Ready?
I know. Funny. No. Oh, we're done. We're done.
You're done. Okay, guys. So have fun, enjoy, and try to solve the previous one too. Not to forget. Okay.
Of course. Thank you.
Okay. You